So then we can basically see how things are differing from what actually happened to what we were expecting to have happen, okay? And we're going to have to compare both percentages and the regular numbers. Here's example 1. Okay, so chi-squared goodness of fit test. All the directions are at the top, so we're going to do this on the bottom. First thing we have to do is verify that the observed frequencies were obtained from a random sample and each expected frequency is at least 5. So, I did not put the results down there. My bad. Because we're using the results from the last one. So, let's see. Let's just quickly write it out. It was 5 things, right? 1, 2, 3, 4, 5. We had an accountant. We had doing something by hand. There was by computers. Having a friend do it, or family member. And having a tax preparation place do it. And that was 61, 42, 112, 29, and 56. And that's our expected, or observed, sorry. And then we also figured out the expected from the last one, which was 72 and 60, 105, 18, and 45. All right, so see that every, it does say in the problem that it was random. And then do you see how every single one of these is at least 5? So we know it's big enough. All right, so let's do the null and alternative. Okay, so the null is taxes expected. I'm just going to write down the percentages that we expect because I'm just writing this in shorthand. 24%, 20%, 35%, 6%, and 15%. That's what we're expecting. And the H sub A is that the percent is not what we are expecting. So the claim in this case it will always be that H sub O. Unless, of course, somebody is specifically saying, this company expects this, and we think they're wrong, you know, then I guess it would be the other one. But usually it's the H sub O. And everybody understands that if you were doing a free response question, you wouldn't write it this crappily, right? You'd actually write out like 24% of people do their taxes by accountant, you know, and like actual sentences and stuff like that. Okay. Next, we've got to do, let's see, alpha is right there, so we got that one taken care of. Degree of freedom is k minus 1, where k is how many categories you have. So you might want to write this up here, that k is categories. So our degree of freedom this time is 4. And now we're going to look up stuff on the table. Now, chi-squared test actually doesn't look like a bell curve. It looks like something else, which is very strange. It looks like kind of like a bell curve that is skewed right, so it's got like a kind of like a large bit here and then like a tail going off this way, and that's how a chi-squared test always looks. And this one is going to be two-tailed. Or is it, no, why do they have it as a right-tailed? I assumed it was two-tailed because it's basically like it equals to or not equals to, right? But I must be wrong. I haven't done this part in a long time. It looks like it's only right-tailed. Let me check the other ones to make sure. Right-tailed, right-tailed, right-tailed. It's only right-tailed. All right, well, guess we don't have to worry about that a lot then. So here, maybe because like this is how solid it is, the null down here is how solid it is, and this is like the outliers out here, so something being very different. Do you see what I mean? So we're doing a right-tailed test. All right, so let me show you how to use this table. This tells you your degree of freedom on the side, which in this case is 4. And then you need to look up, it actually reads from the right instead of from the left. So on this one, you will only look up, what is it, point 0.01. 13.277. Yeah. Okay. And now we've actually got to do the test. So what we have to do is we have to figure out the O minus, so to get our chi-squared number, and the way you can delineate it instead of just making it look like x squared is make it kind of look like a fancy x with like kind of like almost a curve to it. That's how, because it's a Greek letter called chi. And that is the summation of all of the O minus the e's squared, all divided by the e's.